Hello, everyone. So today, Redi is going to tell us about infinity operads, part two. Okay, please
Okay.
take it away.
So this is the part 2 of the previous talk. So we are concerned with this question: what is an infinity operand? And what we've been presenting is this model that appears in this paper. So let me say this is joint work with my former advisor, Özgün. Okay, so by the end of the last talk, so we sort of answered this question, but sort of in a rushy way. And so let me perhaps point out a few things on our model and why we think it's a good model. And so this talk, I'm going to skip some of the sort of very technical combinatorial things and more point out what's the idea of the project and what are supposed to be the applications, etc. So last time we constructed, so remember we defined a category of sets. So the objects, sets, and morphisms, sort of these mappings where Lx is set of finite sequences, which means, right. So we are dealing with this category of sets. You assign to A a sequence in X, and you compose by concatenation, etc. So this is a Kleistli category. Then we built a nerve functor from the category of operads to a category of simplicial lists. And so let me just quickly revisit what this was. So take an operad P, and the idea was that you do the list nerve, and the n simplices are, I mean, informally speaking, so let's say like this, so n-leveled trees of operations in P. Okay, and of course, I have to put some quote marks here. Okay, so let's do a quick figure. So for instance, if n is equal to 2, what's a two-level tree, right? So say something that looks like this. Okay, so the configuration of operations in P. So let's say this is like G, F1, F2, and these colors are A1, A2, A3, B1, B2, and C. And so the idea of levels is that if we take the standard simplex delta 2, and we can represent it like this: 0, 1, 2, and we have the morphisms. And now our tree is sort of leveled according to the 2 simplex. So we keep track of these. And there are operations in each level, etc. Okay, and the sort of similarity with dendroidal sets was pointed out, so I will say something about that. Okay, so now how do I encode this notion of level tree? Okay, so we encode it by sort of looking at the layers and writing them as functions of ordered sets. So for instance, we have this A1, A2, A3. This maps into B1, B2. So A1 and A2 go to B1, as the picture suggests, and A3 goes to B2, and then the set C. Okay, so this is a 2 simplex in the nerve of the category of finite ordered sets. And so we have this sort of correspondence between level trees and simplices of this category. And right, so let me write just a quick well, definition, I guess. So a simplex here is said to be rooted if well, so we represent it, right? It's a simplex. So if given this, we have that the last vertex goes to a unique point, which means like the very last bit of this has to be a singleton set, which means this really encodes a tree because you end with a root. So it's a notion of rooted tree, right? So the notation we use is we just put root here to suggest that we are encoding a tree. Fine, and now how do we sort of make sense of this? Right, so we define, we have this notion of multigraph. So this is defined to be a functor from the truncated delta category to list, which is operatic. So I'm not going to recall what this is. We can say it in other words. So we have 2 sets, a set M0 and 1. So this is, we can think of it as sort of operations and colors. And for each operation, we have the source, so we have the target, which is D0. This is a function. And we have the source, which is D1. This is a listing. And we have the degeneracy as 0, which is, again, a function. So this is just a configuration of some operations with source and target, sort of like this picture. Okay. And so the first thing to point out is that this is a simplicial notion. Okay, so a key to our approach to infinity operads is that we work simplicially. Notion of multigraph here is just a simplicial notion. Nothing to do with trees or anything. Okay. And now, I mean, we have a category of these multigraphs, so have this free forgetful adjunction, multigraphs to operads. So we can do a forgetful functor. What does a forgetful functor do? Take an operad, let the operations be M1, let the colors be M0, source target identities. Right? So you have this forgetful functor, call it U, and we have a free functor here. So I'm not gonna, so in the paper we do this rigorously, but kind of intuitive. You have, say, some configuration, I don't know, say a picture looking like this, operations and colors, you compose everything until you get an operad. Well, this is similar to the where you have a graph and you do the free category, right? Right, so we have this now. Now we construct, so the way we do the nerve is the following. So number one, take a simplex, I don't know, in simplex, which is just a chain of ordered sets and order preserving functions. And define an associated multigraph and it's really the picture there. Okay, so you have the function, you have your simplex, just write it in this form. You can define operations with sources, the preimages, and targets, well, the colors themselves. It's just you can do that always. And then two, you can define an operad T alpha, which is the free operad on this multigraph. Just you compose everything. And then three, you say this, you define the list nerve of an operad P, you define an n-simplex to be sort of, you take all of these level trees, these have to be rooted, and you do maps of operads T alpha to P. So it's sort of, this is the order of things. Okay, so when you see this expression, there is a similarity to the dendroidal nerve, right? In the sense that you're taking trees of operations, but if you look at the construction, already a key difference appears, is that in the dendroidal approach, okay, what's the dendroidal approach? I haven't said anything. So there is an approach to the theory where you take trees, right, and you take free operads and you do something similar, except what has happened here is that trees, the notion of tree as a combinatorial expression has been relegated to a heuristic level. Okay, so that we can draw, for instance, these pictures. Otherwise, I mean, on the formal level, we are working with these simplices, we are encoding them as these multigraphs, doing the free operad construction, which is adjoined to the forgetful functor, and then defining this. Okay, so there is a key technical difference here already. And I must point out, again, this notion of multigraph is really something simplicial. It has nothing to do with trees or anything. It's just that any tree can be recorded as a multigraph if you want to. Right. Now, let's quickly draw a picture of how the simplicial operations work. So say you have, let's draw the same picture. So say we had this. So we have G, F1, F2, A1, A2, I don't know, A3, A4, B1, B2, C. So say this is a 2-simplex in the listener of an operad. How do you do faces, for instance? So you do the face, so let's do D0. Right, so going back to this, let me draw the same picture, sorry. So there is just the A3 here, not to be confused. So when we do D0 here to the ordered simplex, you delete this. And that means you delete this part. So you are left with only G. So these are just our regular simplicial operations. And D1, like it's supposed to, it acts by composing. So if I did D1 on this, I will compose these two maps to get something here. And the way this acts here is that you compose these operations in the operad. So what you get is this. So A1, A2, A3, C, and here you do G composed with F1, F2. So the interesting thing in this approach happens when you try to do D2. So when you do D2, for instance, to this simplex, you will cut this root. So you do D2, you will cut this. So you are left with things which are not anymore rooted. Okay? So what happens when we cut this last layer? We are left with a sequence of things. So this will be A1, A2 to B1, F1, and A3 to B2, F2. So this is where this notion of listing is useful, because we do say that the D2 face takes this simplex to this sequence of 1 simplex. So this is how the listings work. This is how the simplicial identities work. And so this nerve is sort of well defined. You can check. I mean, it's not difficult, right? And so that this is how this functor works, right? So any questions?
You have conditions. If you remove the rooted condition from your definition, you still get a reasonable simplicial list. You know conditions under which those things will be the image of an operad.
Okay, I'll come to that. Okay. It's the next thing. I mean, right. So if you remove the rooted condition, you get a simplicial set, actually. which is the nerve of the envelope.
Ah, okay.
So that's what I'm gonna say next. Right.
Because like rooted forest sets show up in some of the dendroidal literature.
Yeah, I mean, keeping track of levels seems to be sort of yeah, keeping track of levels in things, it's a theme. So yeah, I'm not surprised that it appears a lot. So let me just quickly restate the nerve theorem and just very quickly tell you how it works. Just brief sketch of the proof. Yeah. This should go. Okay, so last time we ended on the statement. So our first theorem in this approach is that so let X be a simplicial list. Then X is isomorphic to list nerve of P for some operad P if and only if X is operatic and the simplicial set Lx is a quasi-category. Sorry. Getting ahead. So is isomorphic to the nerve of category, to which I will just say is a category. So there is only one thing for me to explain here, which is what is Lx. So here, L is the Kleisli adjoint, so which means we go from list to set, and we take a set X to just the set of lists, the set of sequences. Now so what that would do, so if I have X some simplicial list, the simplicial set Lx has as n simplices the lists of n simplices of this. So what this does, I mean, so by functoriality here, we obtain a functor. You get it from simplicial list to simplicial set. This is an important functor. So what you do, like if you have a simplicial list, like say over there, some of the simplicial operations, phases or degeneracies will be listings. And now if you do the simplicial set of listings, those listings become functions. Okay, you get a simplicial set, that's what happens. And so let's quickly say why this theorem makes sense. So let me sketch proof. So one direction is already obvious, or not, but yeah. So let me say something. So this direction, let's consider it done, or well, later. So I will do the other direction. or sketch the other direction. So if I have a simplicial set, a simplicial list which is operatic, and I know this is a category, how do I recover an operad where such that this X is precisely the nerve? It's not difficult. I mean, so we define the operad P with colors just the zero simplices, just like we proved the nerve theorem for categories, you know, and operations just the one simplices. And because we know things are operatic, if I have an operation which is a one simplex, I'm going to let D0F, so this is the target assigning space, and this will be in X0. So, and I define this to be the target of F. And now D1F lands into the list in X0. And I just say this is the source. And if I have whatever color in X0, what we do say is that this S0A, which is the degeneracy, it lands in X1 because we are operatic. So this is the identity operation. Okay. Now, why does this give us an operad? I have to tell you something about composition, and I can do this very simply. So say I have an operation G, and let's say it goes from B1 to BK to C, and say I give you also operations F1 through Fk, which again have targets, say, A1 up to AK. So these are sequences. So if we have like a configuration, how do I compose? Okay. And so we use the Lx being a category. How? So this gives us in L of x, so in L of x we will have the following. Okay. So we will have, now the zero simplices are sequences of zero simplices. So I can write operations, sequence of B's to C. I have the G here. And then let me define just the A is the concatenation of this. So A1 concatenation, etc. AK. And a one simplex in Lx is a sequence of one simplices according to this. So I have a sequence F1 through Fk, which I will just denote underline F. So this configuration gives us a composable pair of one simplices in Lx. But I know that Lx is the nerve of a category. So I can always provide a composite here. So there is a unique H here such that this is a two simplex. And so this is how you define the composite. So this provides composite. Composition of G and the sequence of f's. And yeah, so this is pretty much how you construct an operad out of this data. And so what we do is that we make a definition out of this, and we say that a simplicial list, right, to here, if X is operatic and the simplicial set is a quasi-category, then we say that X is a quasi-operad. I guess you have to omit some of the writing here, but that's what it is. Okay, so again, simplicial model has to be pointed out. So now I will address Walker's point. Which is the following. So we have in operad theory something we call monoidal envelope. So terminology is due to Lurie, but the notion is not due to Lurie. So let P be an operad. So define L of P to be the following turns out to be monoidal category. So objects of LP are sequences of colors of P and morphisms of LP are sequences of operations of P. Well, it's better explained with a picture. For example, this sequence of operations, say F1, F2, F3, so this is a sequence of operations in P. It's a morphism in the L category between the sequence A1, A2, A3 and the sequence B1, B2, B3. So that's how it works. You just take sequences of things and you consider them as objects, and sort of any sequence of operations gives you a morphism. Okay, now what's the thing here? So I mentioned this last time. Now we have operads and we have monoidal categories. This is monoidal by concatenation. So now we explained how, given a monoidal category, we can form this operad. So V monoidal category, and sort of we form this operad with operations being just like morphisms of this form. Right? Okay, so it turns out that this monoidal envelope construction is the left adjoint to this. So that's how it works. So L and this is an adjoint. Pair. And what we get is the following. So we have this. We have a commutative square of categories and functors. So we have operads, and we have, let's go to categories with L. So this actually lands in monoidal categories, but it doesn't matter. So we have simplicial lists, and we have simplicial sets. And the way this functor was defined is just lists of simplices. So this is coming from the Kleisli adjunction. And this is coming from the adjunction with the forgetful functor here. So they're sort of two different things apparently, but this commutes. So you do the list nerve. So this commutes, of course, up to isomorphism. And so this is the sort of connection you get here. Now going back to Walker's point, so we can prove the following. It's actually sort of entailed by this in some sense. So you take an operad P, do the monoidal envelope, look at the nerve, and say an n-simplex in the nerve. These correspond precisely to take not necessarily rooted alphas, which parameterize forests, and do this. Yeah, n here. Yeah. So this is, I mean, pictorially and intuitively fairly straightforward. So we can explain it with a little picture. So let's say you do LP, right? I mean, look at this picture. So this would be in nerve of LP1, right? This is just a morphism. Now, anything in nerve of LP1, we know is a sequence of operations. So you can sort of split this into some trees, or you can depict it as a forest, which can always be regarded, I mean, can always be encoded as a function from leaves here to leaves here, order preserving. So this is how you get the alpha. So you have like if you have more things here, you can create the indexing alpha appropriately.
And it follows formally because the M and T constructions both preserve coproducts.
Yes.
Yeah. Okay.
I mean, that's how it is in the paper. I'm just saying. Yeah. I'm just saying, like, this is very intuitive thing. Actually, yeah. So this is a very important property because it sort of shows that the Kleist junction here is an extension of the monoidal envelope here. This is rather surprising because this is defined as a right adjoint, this is defined as a left adjoint. But I'll just say it in words. This becomes also a right adjoint when we change morphisms here, but I'm not going to go into that tangent. Yeah, anyway. So yeah, it's important to me because, I mean, this is sort of, right, the correct kind of L to consider. And so it, yeah. Right. Okay, and so this also proves the other implication in the nerve theorem. Yes. Anyway, so this is the main idea. So another thing to point out besides this is that we have this inclusion of categories into operads, and we have an inclusion of simplicial sets into simplicial lists. And of course, our nerve here extends the nerve here. So this is, I hope, fairly simple because in our nerve, so say you have a category, you consider it as an operad. The only way you can map a tree into a category is if the tree is sort of linear like this. And so you end up with the nerve. So also have this. Okay. So these are really some first constructions. And I want to make two more points. So we have four main theorems in the paper. One of them is the nerve theorem. And I'll briefly explain or just point out some interesting stuff. So this really takes some effort. And I will just state the result. Okay, so there is a full subcategory F in S list such that S list is a presheaf over the base F.
Just as a clarification, is that an isomorphism or an equivalence?
Equivalence, yeah. Well, this is an equivalence of categories. So perhaps I should say this. Yeah, so this has been very surprising for us because S list is just a category of simplicial objects. And having a presheaf structure, moreover, we sort of don't know much about what the base looks like. We just derived it kind of in abstract fashion. I mean, so I'm not gonna say, I mean, the proof is very combinatorial, etc., long. There could be shorter proofs. I don't know about it, but this is true. And okay, one important corollary is that S-list is complete and co-complete. Yeah, I'm just gonna leave it here because there is nothing I can do in this limited amount of time to explain how this is true. So the sort of a consequence of this, but not quite. So this is main theorem number 2, and main theorem number 3 says that there is a full subcategory I'm calling it epsilon of operatic simplicial lists such that, first of all, operatic simplicial lists are a presheaf over this base. Okay, so far this is a, I mean, it doesn't take much to go from here and derive this, okay? But we have the following. So theorem goes on. Moreover, epsilon can be described as follows. So the objects is the operatic. Yeah, so these are, you take, so these are functors into list, but we sort of restrict. Yeah, so you say that only the last phase is a list. All the others are functions. It behaves like a simplicial set for all other operations except last phase. Yeah, so you restrict that. I mean, and you can show actually for any restriction, I mean, take any restriction you want for things to be functions, you do get a presheaf structure on the restriction. You just restrict base elements to operatic base elements. That's what happens. But for the general case, we don't have a combinatorial description. Like, what are these things? But for the operatic case, we have a combinatorial description. So the objects of the base are sort of, can be defined to be simplices here. So you let n vary. And these are basically, heuristically speaking, level trees.
Forests, or are they assumed to be rooted?
Rooted, yeah, rooted. So objects can be interpreted as level trees and morphisms. So this is better done with a picture, but I want to sort of. So if I had like an n simplex, and if I had a k simplex, okay, so this is
Sorry, I think your mic is
I don't know how to fix it though. Right. How about now?
Yeah, I think.
Yeah, okay. Yeah, so remember these things, the last bit here is just singleton set. So, and this is in an n simplex, this is a k simplex. Right, so I have to tell you what a morphism between these is. So there is a morphism from beta to alpha, the pair, where theta is a simplicial operation, so which goes from k to n. So this is just a simplicial operation in delta. And A is an element of the set A theta of k. So you look at the last vertex. So it's a pair like this. So this is the combinatorial description of this category. Now, in 3 pictures, what is this? Okay, so let's do an example. So say I have alpha being our running example. Put one here for consistency.
These aren't subject to any conditions, or
No condition. Ah, okay, sorry. Yes, such that. Okay, oh, should go on. Okay, here, such that. I forgot. Beta is, you apply theta to alpha and then restrict to A. So let me explain what this is. Yes. So say this is alpha, which means, let's label these again. So I'm writing this in tree form. And the way you get a morphism into alpha is you apply some simplicial operation. So say we do the D2 phase, which is the interesting case. So when you do the D2 phase, I mean, first to alpha as a simplex in delta plus. Okay, so you kind of cut the root. So you do the D2 phase, and what you're left with is a sequence of things. And then picking an element of A theta k means you choose one of these roots. So the operation of doing D2 and choosing B1 gives us a morphism from the beta here to the alpha here. So this is like a simplex category of sorts. Okay? So we record level trees and operations which consist of sort of putting a rooted tree into the other tree. Okay. Yeah. And this again takes, I mean, some work to prove. I mean, as I said, this takes work. Deriving this from here is not difficult, but then deriving this also takes some work, like the explicit description. And now what I want to just point out, okay, and which is, I guess, a point of novelty, is that this is combinatorial. Okay, what we are doing is simple, like simplices of finite ordered sets and sort of performing simplicial operations and choosing elements. Okay, there's nothing else. So in the dendroidal approach, so let me just, for the sake of comparison, so you define this category omega. So the objects are rooted trees, and these can be anything. So these are not leveled, for instance, something like this. And the morphisms, so say I have a rooted tree T and a rooted tree S. So you define morphisms from T to S to be morphisms of operads between sort of free operad on T and free operad on S. This is the dendroidal approach. And then you define a category of dendroidal sets where you do just the presheaf on this. Now notice, for instance, I've done an example here. Say this was my tree S, and I will have, say this is T. I have a dendroidal operation from here to here. Now this description is not combinatorial in any sense. And if you think of trees, I mean, it's not clear how in the language of trees you would combinatorially describe morphisms like this. So this is, I mean, you have faces, degeneracies, and things like that. This is a good framework, but it's not combinatorial in the apparent sense of the word. Okay, but if you look at this description here, so we restrict to level trees and some particular simplicial operations. This is purely combinatorial. So yeah, there is a difference here. Even though the two approaches have similarities, of course, we are studying the same object. So everyone is looking at trees of operations and things like that. No, there is, I mean, there is no, first of all, this is unleveled, so we don't really have such an S to begin with. I mean, yeah, so that's a kind of a good question. So anything you can encode with a tree like this, you can encode by a tree like this, because you can always send this to the identity and it doesn't affect what you are recording, right? And now from here to here, combinatorially, you apply the D1 operation, which squeezes the level. And, well, you're not doing anything with the root, so if we call the root R here, we just do this.
It might be worth mentioning that this actually already shows up in the classical approach to operads. There are two ways that you can define operatic composition. You can either define it at one leaf, or you can define it the way Redi did with G composed with F1 through Fk, and then the one-leaf compositions where you plug in ahead.
Yeah, I mean, this is sort of a partial, like a composite along a single leaf, but you can always transpose it to composite of like this uniform, you can add identities all the time. So given that we know this, level trees are enough to encode the structure of an operad. That's the content of the Nerf theorem. And it's not just about what trees you choose, it's about the morphisms between trees. I mean, here it's like all morphisms of operads between the free trees. We don't know what those are. And we sort of know, but it's hard to think. Here it's like, okay, apply simplicial operation, choose root. Very simple to kind of depict, actually. So this is what the simplicial approach actually provides. And so we have a dual perspective, really. Like, we have two equivalent categories. So the right-hand side appeals to the tree intuitions, etc., etc. The left-hand side appeals to comparison with classical simplicial set theory. And we kind of use both to derive theorems. But they look like very different things anyway. So yeah, this was the sort of one of the roughest combinatorial things to prove. And how much time do I have? 26 minutes, very good. Right, so yeah, and having a presheaf structure is important because you can do Yoneda extensions and all of that. So for instance, let me another way to define the nerve, say the following. Put this in as an example. Now we can take that category there. We have the Yoneda embedding into operatic simplicial lists, and we have operads. We can create this functor, take alpha to the operad T alpha that we had, and this automatically induces the nerve and automatically guarantees, well, I'm calling this fundamental operad, but anyway, so it's a free operad construction from simplicial lists, the operatic ones to operads. So we do get constructions like this kind of for free, right? So the nerve can be reinterpreted this way. So we could have begun by proving this theorem and then say, okay, this is the definition of the nerve. But as we have seen, like creating the T alpha already has the simplicial sort of intuition to it anyway. But you get things like this. And now I want to just point out a little how this relates to the classical presentation of infinity operads. So
By the classical presentation.
you mean, yeah, it's what I
or
simplicial operads. Sorry, classical presentation. You put lure in that? I mean, I challenge you to bring 10 classical theorists who would be able to write down Lure's model. I'm sure you can't. Yeah. So let's say a few words about this. So classical presentation of infinity operads, and I will just say a theorem. This is, of course, not even close to being due to us. This is classical. Okay, so I'll state a brief form of it, but let me denote by op delta. So this is the category of simplicial operads, by which I mean simplicially enriched operads. It's just like simplicially enriched categories, simplicial categories. This is unfortunate confusion, but anyway. So there is a model structure on simplicial operads in which the fibrant, cofibrant objects are operads enriched in Kan complexes. And I'm not telling you what the weak equivalences are, etc. So there is a whole, so we have the Bergner model structure on simplicial categories. This is pretty much an extension of that, straightforward. Okay, and but what this tells us, the fact that fibrant cofibrant objects are operads enriched in Kan complexes. So if we interpret Kan complex to be space, it's just saying that, well, this model structure presents the infinity category of operads enriched in topological spaces, which we interpret as a model for infinity operads. So this is the classical theory. All right, now we want to connect our notion of infinity operad, or of quasi-operad that we define, to what is already known. And so to do that, what I will briefly explain is another such schema but now I want to hit simplically enriched categories, and I will define for each rooted tree shape alpha, we can define a simplicial operad which we have called V alpha, and this will induce a coherent nerve functor into simplicial lists, which for free gives us a rigidification of simplicial lists, generating a free simplicial enriched operad. All right, so again, coming up with this, with the correct V alpha, how many hours of meetings did it take? Lots and lots of hours, yeah. And now I will just say what it is, sort of. Yeah, it's sort of. And let me explain where the difficulty was, because it's not just in defining it, it's in proving stuff. So how do we define, so let alpha be in a level tree shape recorded as a rooted simplex in the category of finite ordinals. I will define a set, pick U alpha KM. So these will be, let me just write it down, indexed over, so you do the thick delta N, and you do the M simplices of this, and then, so if alpha is presented as a sequence.
Why is one of your deltas blackboard fold?
This is the thick delta N.
The two categories.
No, the coherent nerve of that. Yeah. The simplicial category. Yeah. So this is the cofibrant replacement of delta N in the model structure for simplicial categories. So I'm using, I'll comment on it later. You take N simplices of that. So now the last vertex here hits one of the N's, and you just do this. So these sets assemble to form. So if you look at the variables, so here we have a simplicial structure because you play with the M, you're just playing with the simplicial. But if you play with the K, because of these type of expressions, you get listings. So yeah, one variable is listing, one variable simplicial, which means I get this. So I can define this to be just let K vary and M be fixed. And what you get is a simplicial list. And then what you do is that you apply the free operad functor. So these will all be operatic, etc., discrete. And you get a simplicial object in operads where every simplicial operation is identity on objects. And so, yeah, you just let this be the presentation for your V alpha. So basically, you define your V alpha to be tau 1 of these thick U alpha. When we think about it, I mean, I didn't use the fact that these are rooted, so I could just do the general forest case.
So what happens to N?
No.
What?
Yeah, okay, sorry. So, okay, so this, yeah, you're right. There is a notation problem. So here I want to send K to U alpha K and leave this open. So yeah, let me just maybe put a dot here or something. And yeah, that's what I want to do. No, sorry. Yeah, I want to send M to letting this vary and be this BM. Yeah, I don't need to write the M here.
I mean, the N somehow comes from alpha itself.
So the M, yeah, so no, I want the K here, sorry. Because, no, yeah, that's what I want. Yeah, sorry. Because the K variable gives us simplicial list in the target, right? And the M variable gives us simplicial object here. So I'm looking at this simplicial object. And I'm denoting it, yeah. sorry, the M here was sort of confusing, but that's what I'm doing. Okay, yeah, thanks for pointing that out. It was written kind of horribly. Yeah, and why precisely this formulation, etc.? It's just, I mean, the relationship with categoric theory. Yeah. And so another sort of theorem that can be proved here, or let me say, what we have is that if I had some simplicial operad Q, there is this. So you take Q, you can apply the L, and you get a simplicial category. And then I can take its coherent nerve, and I get a simplicial set. And an n simplex here is always parametrized by a level 3 shape or a level 4 shape. This. So the headache is or has been in constructing the V alpha satisfying precisely this problem. This is of course natural isomorphism. So this has been a big headache that lasted for a while, but finally, yeah, there is the combinatorics are a little bit involved, but you have this, and now, okay, so we can define this coherent nerve, and because this holds, we have the following, that you have simplicial operads, and you go with the monoidal envelope to simplicial categories, and we can go with the list coherent nerve to simplicial lists, and then to simplicial sets, and then usual coherent nerve. Easy to show this commutes after you know that. And this is again important. Now, you don't have these, like, one very interesting feature of the approach we have is stuff like this. So you have this connection to classical theory, which can be used to derive technical advantages from. And one of them is the proof of this theorem. Now it follows. So if you have an operad enriched in Kahn complexes, you do the coherent list nerve. This will land in quasi-operads. So you take something fibrant cofibrant in the classical presentation, and it gives us a quasi-operad in our presentation. It's an indication that we have the correct kind of stuff. Now, how do you show this? I mean, fairly easily, if we know this. And why is that? Because, I mean, you start with the Q, which is enriched in Kahn complexes. You go to LQ, again enriched in Kahn complexes. Not difficult to show, straightforward actually. Now you do coherent nerve of this. This is now a simplicial category enriched in Kahn complex. So when you do coherent nerve LQ, this is in quasi-categories. So we offload a big chunk of combinatorics to the classical simplicial categories, quasi-category stuff. And now this commutes, so I can do the listener and then do the L. So this gives me L of coherent nerve of Q. These two are isomorphic. So the Q gives me an operatic simplicial list such that the L of it is a quasi-category, which means it's a quasi-operad according to our definition. And so really having these isomorphisms is very important because you can do proofs like this effortlessly. And constructions are what they are. I have to say there are intuitions behind writing down these, of course, which we don't have time to. And I mean, some of these appear in the paper, etc. But really, this theorem is fairly important, and it shows us something that there. I mean, what we conjecture is that this adjunction will actually be equivalence between the classical model structure and we don't have model structure here yet, but conjecture is okay. There is a model structure here whose cofibrations are monomorphisms, vibrant objects, quasi-operads, such that this is equivalence between model categories. So that would prove that our quasi-operads here do indeed model infinity operads. The reason it's sort of believable, even without going into the hardcore stuff, is again, like you think pictorially, you have these coherent compositions of operations given to you. I mean, if you believe quasi-category theory, then this is easy to believe, but this still needs proof, and it takes a fair amount of work because this is technical. And sort of this is one thing to point out. So to conclude, there are two, I think, key aspects to our approach. One is the very simplicial nature of it, which simplifies many things. And the tree, sort of the language of trees, is really just a heuristic to understand things. We're not actually working with trees. Everything is encoded simplically. And yeah, let's see where this goes. Now for, do I have some more?
Just to wrap up.
Am I over time?
No,
I'm sorry.
4 minutes left, but we have
I mean, seminar is on. Do I have 4 minutes or not?
4 minutes.
Yeah, okay. Yeah, so just, okay, today it's like all constructions. If we go back, so we had one running example for the talks. But for instance, I can do the associative algebra, do the list nerve, and do the coherent nerve, where you take any category of spaces and look at it as simplicially enriched. And I can say that a morphism of simplicial list like this gives us the classical notion of infinity space. And something we failed to mention last time is that these are the same, for instance, as monoidal infinity groupoid. And fine, I mean, it's a simplification of homotopy coherence because, I mean, you want to work with this model, the cofibrant replacements are messed up, but here is just morphisms of simplicial lists. It's one thing. And what you hope to get, for instance, in SQL works is that you have fibrations which allow you to do these things fairly easily, etc., etc. So it's desirable, and we expect to replicate sort of the features which make quasi-categories so practical, which are fibrations, for instance, and things like that. So yeah, just I'm gonna finish on that. Thanks for listening.